which is known as Miller indices. So obviously Miller means the name of a scientist, but what are these stuffs? That is what we are interested in. What are Miller indices? For understanding what is Miller indices, you should know what is the crystal plane. So how do I understand a crystal plane? Yesterday I asked you to imagine like a sheet of paper as a plane. Above that we kept another sheet and like that, right? Basically it's an imaginary plane. There is nothing like a real crystal plane which exists. It's an imaginary plane which is inside a crystal, which is there inside a crystal. Okay, it is being assumed that it is there and has all the atoms. So this figure which I am showing you here, all these atoms belong to one plane. So all these is a plane. This is a crystal plane. Now at the same time you can see these three atoms are in this particular direction, horizontal direction. But these fellows I can even assume that they are in a vertical direction, right? I can see these atoms in this direction, downward and then up, all those, right? So the different directions. So the different directions which are there along which the atoms exist. It can be horizontal, vertical, downward, upward, whatever be the direction. That is known as a crystal direction. So crystal plane is an imaginary plane which has the atoms. A crystal direction is the direction which all the atoms are existing. Okay? Not all the atoms, some of the atoms might be existing. Some will be horizontal, some will be vertical, some will be some other direction. So now, Miller, this scientist, he bring in this concept of Miller indices so as to represent these crystal planes and crystal directions. Okay? So, as you know that a crystal obviously has a three-dimensional structure. So, for that reason, there are three numbers, okay? Three numbers, a set of three numbers written within parentheses. These are parentheses or the normal round brackets, okay? A set of three numbers written in round brackets is what is going to represent a crystal plane, a crystal plane. If there are three numbers, a set of three numbers, if I put within square bracket, okay, then it is going to represent a crystal direction. So if I put in round bracket three numbers, a set of three numbers written within round brackets, then you call it is going to represent a crystal plane. Three numbers for the main reason that there is a three-dimensional structure. So along x, y, and z, all three directions. If I put it within a square bracket, that is actually representing a crystal direction. So this is actually the Miller index. So usually we talk about the Miller index with this round bracket. That means we talk about Miller index representing the crystal plane. Okay. So how can we get this so-called Miller indices, the so-called three numbers? So as to put them in bracket and say that this is what is the plane, crystal plane represented by. Okay. So there are a few steps in order to do that. First one is this. Find the intercepts made by the plane along x, y, and z axis. Suppose I take a crystal structure and there is a plane, there is this so-called imaginary crystal plane. We find out at what position on the x or at what distance on the x, y, and z axis is this plane intersecting. So I'll get the value of intercept. Okay, I'll give you an example in the next one so you will understand it. Next, find the coefficient of the intercepts. Basically, it's like if I say intercept is 1 centimeter, that means the plane is touching at a distance of 1 centimeter or 1 unit. Okay, I'll not say centimeter, I'll better say it as unit. If it is 1 unit or 2 unit or 3 unit, then the coefficient is 1, 2, 3. Okay. Next, find the inverse of those coefficients. Find the inverse of that number. After that, very important point, multiply the inverse with the LCM. Okay, find out the LCM. So first is to get the intercepts. From the intercepts, find the coefficient of the intercepts. Next, find the inverse. Next, find the LCM of whatever you are taken as the inverse. Multiply with the LCM. Okay. And whatever numbers you get, just put within the brackets, within the rounded brackets or parentheses. That gives you the Miller indices. It is denoted by like this. Within rounded brackets, HKL. Main point to be noticed, there is no comma separately. HKL. H obviously with respect to x direction, K with respect to y direction, and L with respect to z direction. I'll move to the next slide and then give you an example. So here is the case. Obtain the Miller indices of a plane with intercepts A, okay, A, comma B by 2, comma C in a simple cubic unit cell. So what are we being given? We are given the intercepts A, B by 2 and C, right? And we have to find the Miller indices. So let's do that. So what we do is this. So this A is for x direction, B by 2 is for y direction, and C is for z direction. So we'll write it like this. X is to y is to z is equal to A is to B by 2 is to C. Okay. Now, it is mentioned that it is a simple cubic unit cell. So simple cube or cubic system, you know that A is equal to B is equal to C. What were these A, B, C? These are the lattice parameters. These are the lattice parameters. So A is equal to B is equal to C. So for that reason, what happens? If I substitute this back, it becomes A is to A by 2 is to A. So A is common. I can get rid of the A. So now the intercepts become 1, 1 by 2, 3. Okay, 1, 1 by 2, 3. These are your intercepts. Next step is to take the reciprocal. So what is the reciprocal? Reciprocal of 1 is 1. Reciprocal of 1 by 2 is 2. Reciprocal of 3 is 1 by 3. What is the LCM? What that is the next step. LCM is 3. LCM is 3. Multiply each of these numbers by the LCM. What do you get? So 3 into 1 gives you 3. 3 into 2 gives you 6. 3 into 1 by 3 gives you 1. So these are your final numbers 3, 6, 1. All you have to do is next put them in rounded bracket. Just give space in between the numbers. Don't put any comma. I'll just repeat this, how you have to do it. You have been given these intercepts for an example. This is just an example. Okay. A, B by 2 and C. This is a crystal system and you are being told it is a simple cube. So first you will write it as each is for each direction. So A is for X, B by 2 is for Y and C is for Z direction. So you write it like this. X is to Y is to Z is equal to A is to B by 2 is to C. Okay. Next, what do you have to do? You know that it's a simple cube. So for that reason, it is A is equal to B is equal to C. A is equal to B is equal to C. So what happens here? Instead of B also I can put A. Instead of C also I can put A. So it becomes A by 2, A. Okay, sorry, it's a, sorry, yes, correct. So actually it is 3C. Sorry, I made a mistake. It is 3C. 3C. Okay, I made a mistake of writing it. It is A, B by 2, 3C. Okay, A, B by 2, 3C. I deliberately needed a number which becomes like a fraction. So that reason it was. So A, B by 2 and 3C. Sorry, A, B by 2 and 3C. Okay, now A, B, C is the same. So I'll get it as A by 2 and 3A. So A is common. For that reason it becomes 1, 1 by 2, 3. Okay, 1, 1 by 2, 3. Next step, find the reciprocal. So 1, 2, 1 by 3. Next step, find the LCM. LCM is 3. Multiply each of these number with the LCM. So 3 into 1, 3, 3 into 2, 6, 3 into 1 by 3, 1. Final, you will get 3, 6, 1. Main point, don't put any comma, give a space. If you don't give a space, it looks like 361. That should not happen. You should give a space and put the value within bracket. Okay. Now, next, what are the different properties? Obviously, there will be a question, why do you need to understand about a plane? Why do you need to understand this? I will come to that application maybe by next class. If you don't know maths, I can't say anything, sorry. If you take reciprocal and then LCM will be 3. I am sorry, I can't teach LCM and HCF here. You are supposed to learn all these things in school. What all such silly questions I will not answer. Let me make it very clear. And I can't spoon feed. Let me make it very clear. You people need spoon feed. No, you have to come out. If you have to do engineering, you cannot be spoon fed. Forget about Cerilac or whatever, Horlicks and all those things. So what are the different properties of Miller indices? Very important. A plane which is parallel to one of the axes will meet that axis at infinity. What does it mean? Suppose I have a crystal plane which is parallel to x-axis. It is obviously not going to meet the x-axis. It will meet the axis at infinity. I will say it is not going to meet, or it is going to meet at infinity. Okay. Now, another important point. Equally spaced parallel planes have same Miller indices. Suppose I have something like 1, 0, 0. That means a plane which is having an intercept in x-axis. It is in y-axis and z-axis. It doesn't have an intercept. It is meeting at infinity. Okay. 1, 0, 0 is a plane. 2, 0, 0 another plane. 3, 0, 0 another plane. Correct. So then what happens? All of them are equally distant, right? 1, 0, 0, 2, 0, 0, 3, 0, 0, correct? So equally distant plane will have same Miller indices. So I can represent all of them with same value 1, 0, 0. So 1, 0, 0, 2, 0, 0, 3, 0, 0, 4, 0, 0, 5, 0, 0, all are same. I can say it is a 1, 0, 0. Okay. Next, suppose there is a negative intercept. Because you know that there are negative x, negative y, and negative z dashes. Suppose there is a negative intercept, then you will put a bar or a dash line over the number. So instead of 1, 0, 0, it becomes bar 1, 0, 0. Okay, I couldn't put the bar exactly above. I just written it like that. Actually, when you write, it should be in a paper or something. When you write, it should be above 1. You should put the bar, and there should be space. Obviously, 0 and 0. Okay. Now, this point is very important. You need to remember. If HKL, so that is how we are denoting these Miller indices, right? So if HKL are the Miller indices, then the intercepts made by the plane with the different axes, the 3 different axes of x, y, z, okay, the intercepts made will be A by H, B by K, and C by L. What is A by C? ABC. ABC, already you know that those are the lattice parameters, or you also call as primitives. ABC, now onwards, ABC, alpha, beta, gamma, you should remember. In addition, you have got another thing, that is HKL within bracket, that is the Miller indices. So intercepts will be A by H, B by K, and C by L. So I'm going to show you some examples of the plane. So this is your 1, 0, 0 plane. This is x direction, y direction, z direction. I have put the unit cell. Okay. I considered this plane on this face, this side of the cube. What is happening with this? It is touching only the x-axis. It is not touching y-axis or z-axis. This shaded region is touching only the x-axis. I assume that this much distance is of 1 unit. Okay, when I take a unit cell, whatever length it is, be it one, when you draw a cube, obviously you take a scale and you draw maybe 1.5 centimeter, 2 centimeter, 3 centimeter, whatever you take. That is considered as 1 unit. Whatever your scale is, that is 1 unit. So x-axis intercept is 1. Y-axis it is not intercepting, but it is parallel to y. So you will say it is meeting at infinity. So intercept is infinity. Z-axis also it is not meeting. So that means it is meeting at infinity. Okay. So just what if you have a book, you can write down. So x-axis intercept 1, y-axis intercept infinity, z-axis intercept is infinity. You take reciprocal, what happens? You will get 1 by infinity, 1 by infinity, right? What will be the value? 1, 0, 0. LCM, obviously 1, multiplied by 1 throughout, again you get 1, 0, 0. That is your 1, 0, 0 plane. Now this one, the next one, immediate one, what you are seeing is it is touching in the y-axis but not in x and z. So you will get it as 0, 1, 0. But what about this fellow? Like a triangle I have taken, you can see that it is touching at x-axis, it is touching at y-axis, it is touching at z. All three directions it is touching, and all at the same distance. That means the entire same length of the cube, entire length of the cube it has taken. So that means equal distance of 1. Intercept will be x-axis intercept 1, y-axis 1, z-axis 1. Take reciprocal, then also 1, 1, 1. LCM 1, multiply by 1, again 1, 1, 1. Okay. So 1, 1, 1 plane it is. Alright. Now what about this fellow? I will come to this plane F which I have shown you. What has happened here? X-axis it is not touching. The shaded region, we are talking about the shaded region. X-axis it is not touching. That means infinity. Y-axis, infinity. What about Z-axis? It has not come till this full 1. But it is somewhere in between, right? So it is at a distance of half unit. So when you write the intercepts, how it will be? For x it is infinity. For y it is infinity. Z-axis it is half, 1 by 2. Next job, find the reciprocal. 0, 0, 2. LCM 2. Multiply by 2. Again 0, 0, 2. So this is a 0, 0, 2 plane. Okay. Moving on to next very important factor. So this is a small derivation as I said in the last class. So now onwards it's up to you how you take about it. I cannot wait for the entire 67, 69 students to write down. So what we are going to do is, suppose I have nearby planes. See, it's not just only one plane which is there in the crystal. There are multiple planes which are there in the crystal. So I can find out what is the distance between these different planes. I will call it by a simple name, interplanar distance. I request all the students to be muted. And don't switch on the video. There will be bandwidth issues. Okay. Now, interplanar distance, in a simple term, you can understand as the distance between nearby crystal planes. Distance between nearby crystal planes. What we are going to do is to find an expression for this interplanar distance. This is very important. As I said, application of Miller indices, interplanar distance, all these things we are heading toward that. Okay, it is natural. If you are somebody who thinks a lot and feels that I want to understand the concept, then obviously you will feel what is the application. So we will come to the application, but before that, let's understand what are each of these parameters. So what I have done here is listen, see this figure very carefully. You need to practice with all these figures and everything. So this is the origin. Okay, I've taken x direction, this arrow x direction. This arrow is the y direction, and this one is the z direction. Perpendicular. This y is also actually perpendicular because this is just 3 dimensions, so drawing was not easy. Now, from origin to x-axis, I consider a point A. From origin to y-axis, I consider a point B. From origin to z-axis, I consider a point C. So A, B, C. I connect these points A, B, C. So I get a triangle like this. This is actually the plane ABC. I'm going to consider the plane ABC. X direction, Y direction, Z direction, take 3 points and connect those 3 points on each of the directions. You will get the plane ABC. Okay. Now next, what are you going to do? You are going to draw a normal into this plane. Draw a normal to this plane. A normal to this plane. This is the normal which you have drawn, ON. ON is the normal. But this normal is nothing but the same as the distance to the next plane. That means it is an interplanar distance. So ON, I have taken a point N here. This is the normal which I have drawn. So this ON is the normal which is same as the interplanar distance. That is the distance to the next plane. The distance between the different planes in this crystal. Okay. Now, next, from N, I connect to A with dotted lines. From N, I connect to B with dotted lines. From N, I connect to C with dotted lines. Next, I mark angle alpha with respect to x-axis or this direction OA. I mark this angle alpha with respect to x-axis. I mark the angle beta with respect to y-axis or direction OB. Angle beta. I mark the angle gamma from the normal with respect to z-axis or OC. So from the normal with respect to each of the axis, you are marking the angles. Okay. And these distances, so we told in the previous, if this plane ABC is having Miller indices HKL, sorry, I should not have put the comma there. If this plane is having Miller indices HKL, then the intercepts is A by H, we told now, A by H, B by K, and C by L. We just see it in the previous slide, right? Before I showed you the planes. A by H, B by K, C by L. I'm going to repeat this figure again because you need to know how to draw it. I take origin, from origin I take X direction, then I take Y direction, and then I take Z direction. Okay, and on all these directions I take 3 points. Point A on X, point B on Y, point C on Z axis. Okay, then connect these points A, B, C. So I'll get a triangle like shape. That is the plane ABC. Okay, and then draw a normal to this plane. Draw a normal to this plane, which actually is the interplanar distance. So this ON, distance ON is equal to D. This is given by the letter D, interplanar distance. Distance between the successive planes, nearby planes. ON. Okay. And from this point N, draw dotted lines to the point A, B, and C. Connect all three. Okay. Next, with respect to the direction from, you are going to draw with respect to the direction of X, with respect to X-axis, ON will make an angle alpha. So from the normal to the X-axis, angle alpha. From the normal to the Y-axis, angle beta. From the normal to the Z-axis, angle gamma. Now suppose this plane has, I can remove this space. Suppose this plane has Miller indices HKL, then the intercepts OA, this distance OA is A by H, distance OB is B by K, and distance OC is C by L. This is very important, you need to remember. Now next, what happens? I can find cos alpha, right? 3 angles alpha, beta, gamma. If this is normal, this angle here, ONA, will be 90 degree. If something makes a normal to a particular line, that makes actually 90 degree. So this is 90 degree. So that means OA is the hypotenuse, ON is the adjacent side. So cos alpha will be adjacent by hypotenuse. That is ON by OA. Cos alpha will be ON by OA. What was ON? ON is the interplanar distance D. OA is A by H. So you will get cos alpha as D divided by A by H. Now once again the same with respect to OB. Cos beta adjacent, this is adjacent with respect to y-axis you are doing. So adjacent by hypotenuse. So what do you get? D, oh sorry, this is adjacent. This is 90 degree. N is here, normal is here. So this is 90 degree. So this OB is actually your hypotenuse. So adjacent, this is adjacent, ON divided by OB, D divided by B by K. Same way, cos gamma, once again 90 degree. not adjacent, sorry, adjacent by opposite side, sorry. I was saying hypotenuse, so sorry. Adjacent by opposite side, right? Cos alpha, adjacent side by opposite side. So you'll get d divided by a by h cos alpha, d divided by b by k cos beta, d divided by c by l. Okay? D divided by c by l. So you get cos alpha, cos beta, cos gamma. You have got three angles, alpha, beta, gamma. You find the cos alpha, cos beta, cos gamma. Okay? Yeah, adjacent by hypotenuse. Opposite side, it will be sine, right? If I take sine, it is opposite by hypotenuse. So adjacent by hypotenuse is the cos. So OL is the adjacent and this is the opposite direction with respect to 90, that is hypotenuse. So d divided by a by h, d divided by b by k and d divided by c by l. Next, what are you going to do? You are going to consider this particular expression. Cos square alpha plus cos square beta plus cos square gamma is equal to 1. This is known as law of direction cosines. Cos square alpha plus cos square beta plus cos square gamma is equal to 1. From the previous slide, I have cos alpha, cos beta, cos gamma. What do I do next? I substitute into this expression of cos square alpha plus cos square beta plus cos square gamma is equal to 1. I substituted it, I get it like this because it was d divided by a by h goes to the numerator, so it becomes dh by a whole square, dk by b whole square, dl by c whole square. All of them added together gives me 1. Just substitute and rearrange. Again, d square is common. So I can take out d square. It becomes d square in big brackets, leftovers, h square by a square plus k square by b square plus l square by c square equal to 1. What do I do next? I move this entire bracket to the right hand side, so it goes to the denominator. So d square is 1 divided by full bracket h square by a square plus k square by b square plus l square by c square. If I need to find an expression for d, what should I do? I should take the square root. It becomes 1 divided by square root of h square by a square plus k square by b square plus l square by c square. I'm going to repeat this again, once again. So you're done with all this diagram, you're got. Then you find cos alpha, cos beta and cos gamma. So it is d divided by a by h. I can rewrite it as dh by a. Okay. It's like 1 divided by 1 by 2 is 1 into 2 by 1, the same way. Or x divided by y by z is x into z by y, the same way. Okay. Now, so I can get this as dh by a. This is d by b by k becomes dk by b. d by c by l becomes dl by c. After this, you should know this expression, that is called as law of direction of cosines. Cos square alpha plus cos square beta plus cos square gamma is equal to 1. Substitute, you will get it like this: dh by a the whole square plus dk by a by the whole square plus dl by c the whole square is equal to 1. D square is common, take out d square. In bracket, you will get h square by a square plus k square by b square plus l square by c square is equal to 1. Next, finally I need an expression for d. So I just move this entire bracket to the right hand side. So it goes into the denominator. So it becomes d square is equal to 1 divided by h square by a square plus k square by b square plus l square by c square. If I want d, I will take square root. I will get 1. Square root of 1 is 1, obviously. So 1 divided by square root of h square by a square plus k square by b square plus l square by c square. This is the expression for interplanar distance in terms of what? Miller indices h, k, l and lattice parameters a, b, c. This is valid for any crystal system. You have studied 7 crystal systems, right? For all those crystal systems, this expression is valid. This is a common expression for finding the interplanar distance in terms of the Miller indices of the plane and the lattice parameters of the crystal A, B, C. Now, what will happen? Suppose I consider the simplest case of a cubic system. You know that for cubic system, A is equal to B is equal to C. So what happened? Instead of this one, what happens to this portion? It will be 1 by square root of h square by a square plus k square by a square plus l square by a square. 1 by a square common I take out and it becomes 1 over 1 by a. A goes to the numerator. Just your rearrangement, you will get this expression. A divided by square root of h square plus k square plus l square. This is just a simple maths. It's just a simple rearrangement. Once you understand from what is the figure and how you, if you have found your cos alpha, cos beta, cos gamma, after that it is pretty simple. If you remember this expression, cos square alpha plus cos square beta plus cos square gamma is equal to 1. Okay.